So we're going to try not to get too delayed on this. So the first talk is by Hilbert von Löhneysen on the multidimensional entropy landscape of quantum criticality.
Okay, perfect. Okay, thank you. Hmm? Okay, good morning. It's actually the fourth time, I think, that I've been here in Natal, and I'm enjoying it each time more, I have to say. In particular, since the IIP has such a nice new building, which really sort of makes me envious about some of the states of buildings that we have in Germany. Anyway, so I would like to talk about the multidimensional entropy landscape of quantum criticality. Let me just explain that actually when you talk about a quantum critical phase transition, you think about a transition at t equals 0. And we of course know that at t equals 0, for most practical purposes, the entropy in a thermal equilibrium has to vanish. So the question is then, what does entropy have to do with that? So the reason is simple. Because the thermal expansion actually is nothing but the derivative of the entropy with respect to strain or stress. So while we can of course determine the entropy at finite temperatures, we find that at a quantum phase transition, the entropy actually is at a finite temperature still very large. It can actually be that the entropy vanishes towards t equals 0 with a vertical slope. That's nothing against the third law of thermodynamics, and actually then tells you that around a quantum phase transition, and that's the story, the entropy has so many, offers possibilities for different states of matter, and of course we know about the state of superconductivity in many systems many quantum critical systems. So that's the story behind the whole thing. And I would like to actually, after an introduction to quantum phase transitions and the thermal expansion, I would like to come to the serum copper gold, which is a canonical quantum critical heavy fermion metal, where we can actually probe the anisotropies by thermal expansion, because you can of course measure the thermal expansion along different axes, and thereby you get an information about the anisotropies even without having to apply magnetic field. And then I come to a second example, which is cerium palladium aluminum, which is actually a kagome system, and we looked at the effect of nearby phases close to the destruction of antiferromagnetism and the effect of those phases onto the entropy landscape. And the work has been done with a number of people that are listed here. So then let's come to the introduction. And what is essential for quantum phase transitions is that you have a competition between different interactions. And the famous example for heavy fermion systems is, of course, the interaction between, or competition between Kondo effect, actually screening magnetic moments, and the Ruhrmann-Kittel interactions leading to an interaction between the moments and thereby stabilizing long-range magnetic order. So both actually depend on the exchange interaction JK, the Kondo effect, but with a different functional dependence. So if at small j, actually the Ruhrmann-Kittel interaction is stronger than the Kondo effect, and so the system tends towards magnetic order, and then finally this turns over, and there's the possibility of having a quantum critical point where the Kondo interaction roughly is of the order of the exchange of the Ruhrmann-Kittel interaction. And that's, of course, the famous Donier phase diagram. Although it's not a phase diagram, it's just a comparison of energy scales. You can have an entirely different version of competing interactions. That is, having nearest neighbor or next nearest neighbor interactions in insulating systems, and we've heard about that. This is sort of the three-dimensional version of this goes in the wrong direction. Three-dimensional version of the kagome lattice, that is the pyrocore structure, where you have neighbor competing nearest neighbor interactions, or you can actually have competition between nearest neighbor, next nearest interactions, even in simple systems such as a square lattice. And this has been reviewed some time ago by Sachdev and Keimer. Now, I mentioned that the thermal expansion coefficient for a certain direction gives the entropy derivative of the with respect to the strain in that direction. So an important ratio that we will consider is actually the Löhneysen ratio between the thermal expansion coefficients and the specific heat, and that is just given by this ratio. And then finally, it is important to realize that there is, of course, difference between strain and stress. They are coupled by Hooke's law, and if you look at that in the Löhneysen ratio language, this means then that you actually do need to know the elastic constants to couple the stress dependence with the strain dependence. Stress is the external pressure you apply, and strain is how the system reacts. Now let's look at the, for example, for a thermal liquid. The thermal liquid shows that C over T is constant, and so ds over dt is also a constant. And if you then look at the thermal expansion coefficient, that is the sigma of the entropy derivative with respect to the stress, and then that actually also becomes also constant. So the Löhneysen ratio, oops, what I'm doing. The Löhneysen ratio for a thermal liquid then is a constant. And it was pointed out 18 or 15 years ago that actually if you are close to a quantum critical point, then you have strong deviations from the thermal liquid behavior. In particular, one finds a divergence of alpha I over T, and this divergence is actually stronger, as it turns out, than the deviation of the specific heat coefficient. So actually, altogether, the gamma diverges, and that can be illustrated by looking at the characteristic energy scale. At a quantum phase transition, there is no energy scale rather than the temperature. So the characteristic energy scale goes to 0, and that means that the Löhneysen ratio, which is the derivative of the energy scale with respect to stress, is actually also going to 0. And this is a typical energy landscape. So if you have a quantum phase transition as a function of control parameter, you see actually accumulation of entropy, as I mentioned in the beginning, at towards the quantum critical point here with perhaps a vertical tangent. And that entails that if you have a transition at, I hate it. If you have a transition at a finite stress, for a critical stress, for instance, then if you are above that critical stress, you will have actually an increase of the thermal expansion coefficient with a decreasing temperature divided by temperature, that is, and below that you have a decrease. So as you pass with some control parameter from this side to that side, you have a sign change of the thermal expansion coefficient, and that is actually shown in the next view graph, where for serum copper 6, these are clear indications of magnetic transitions. They can actually also be seen by the magnetic susceptibility, also by neutron scattering. Even in that particular case, for x equals 0.3, you have nice reflections. I don't know what I'm doing. And on the other hand, if you take so this magnetic phase transition can actually be tuned by the concentration of gold in this particular system, and as you decrease the gold concentration, then the magnetic phase transition goes to 0, and pure serum copper 6 has no transition whatsoever. And if you then take a sample with around 10% of gold, you see there's this increase, this divergence of alpha V. In this case, it's the volume thermal expansion as a function of temperature towards T equals 0. Now, how do we measure the thermal expansion? It's very simple. You just have two plates of a capacitor, and actually as the sample expands, in this case, the capacitance plates approach each other, and that gives the dielectric increase of the dielectric constant, and that's what you measure. And that's a very sensitive technique. It just depends on how close you get the two capacitance plates close to each other, and we managed to get them closer than about 10 microns over a length of, say, one centimeter square. Now, I mentioned to you that we want to measure the thermal expansion, that is the entropy derivative with respect to stress on an arbitrary direction. And if you have an orthorhombic system or a system of higher symmetry, you can actually do away with the tensorial character of the thermal expansion and stress and strain. You can just write this in a vector language, and it makes things much more easy. So, for instance, the hydrostatic pressure in this case is just a body diagonal in the stress space. So this is here for two dimensions in sigma A and sigma B. So the stress in that direction in the diagonal would just be the hydrostatic pressure. But there's another type of stress that is equally important, although not so well known, and that is pure shear stress. And that is actually the difference between two different stress directions, with the condition that if you measure them along two different directions, they should be the product should be 0 if the components vary. So sigma Lm actually picks up the anisotropy and should be 0 for isotropic systems. You can then put that on a three-dimensional map. That is what I showed before. That is the pressure, the hydrostatic pressure, the body diagonal in the A, B, and C axis stress, and these are the pressures that actually are indicated here. These are the pure shear stresses that are perpendicular to the applied hydrostatic pressure. So that's just a definition of the components of the stress. So we actually then measured that. First, the pure, just the stress components, thermal expansion coefficient along the three different axes, and then also the volume coefficient. And you can see for the volume coefficient that actually that diverges more strongly towards T equals 0. The specific C over T, specific heat C over T varies as logarithm of temperature. That's been known for many years, and this alpha V over T varies like a square log temperature dependence. As I mentioned, then of course the ratio of those has to diverge at the quantum critical point for T equals 0. Oops. Now I need your help. This is also a nice location. Okay, thank you. Okay, now if you measure the pure shear stresses, as I mentioned, these are just stresses, stress differences for C minus A direction, B minus A direction, and C minus B direction. And here is something very peculiar happens. While you have this divergence for C minus A and B minus A, you don't actually have that for C minus B. And if you look at the corresponding Löhneysen constants, C over A varies the log, varies nicely logarithmically, and also B minus A varies logarithmically, but C minus B actually becomes constant. It actually decreases a little bit. And this, of course, can be mistaken as Fermi-liquid behavior. But I mentioned to you that actually the pure shear stress components are actually perpendicular to the hydrostatic press. So it means something very different, and that is explained in this picture. Now here I show what actually is observed. This is the measured steep descent of the entropy. That is the hydrostatic pressure, and you see the steepest descent is not proportional or parallel to the hydrostatic pressure, but you have to apply also a certain pure shear stress component, namely sigma C minus A, to actually get reproduce the experimental results of the maximum entropy change. And now if you then look at the plane that is perpendicular to this maximum entropy change, you see that we have this one I just showed you, but there's another component, C minus B, that is very close. Actually, it's almost perpendicular to this nabla S dependence, and that means actually that the entropy for this particular stress component, pure shear stress, doesn't change. So it's not that you're observing a Fermi-liquid behavior, it's just you are stuck at a certain entropy value. And this is illustrated in this picture here. This is the effect of hydrostatic pressure. This is the effect of maximum entropy change. And this is the pure shear stress parallel to C minus B. And so you can actually picturize that. That's the thing you want. You have the maximum change of the entropy. Oops. The maximum change in entropy. And this is then the pure shear stress that actually tells you are walking actually at a constant entropy line in this entropy landscape. And the final question now is, what is actually the significance of the direction of the pure shear stress sigma Ca that actually produces this additional change of the entropy with respect to hydrostatic pressure? And for that we actually were fortunate to actually go back to old Newton scattering data. The reference is not even given. In essence, you see inelastic fluctuations that have this type of behavior, which is almost a one-dimensional structure in K-space. So this is the A and C direction in K-space. And a one-dimensional structure in K-space, of course, corresponds to a two-dimensional structure in real space. So what that amounts to is that you have these rod-like structures here, and they translate into planes that are almost perpendicular to each other. And what this pure shear stress does is actually it tilts those two planes of quantum critical fluctuations against each other. And I think this is one of the first examples where one actually has related a geometric property thermodynamically to the microscopic observation of the geometry of fluctuations. So with that, I come to the other system, cerium, palladium, aluminum, which is a kagome structure. We've seen this picture before, and it's actually not a real kagome structure, but the structure, you can see it here, is a little bit corrugated. It should be actually straight lines. And the magnetic structure, as determined by Döni and company, suggests that one has nearest neighbor coupled spins that are ferromagnetically coupled, and next nearest neighbor coupled spins that are antiferromagnetic coupled. So they're in between. There are then atoms that are cerium atoms that get the different information from these chains and from these chains, with a net effect of 0 concerning the Riemann-Kittel interaction. And this has been nicely worked out by Claudine oops. I'll come to that later, but I just wanted to show you something different. This is usually called a kagome structure, and what I discovered a year ago is this same kagome structure on the floor of a church as a floor tiling with a kagome pattern, and that's actually the church Basilica San Clemente de Laterano in Rome. It's a basilica that is 2,000 years old. It has 3 different stories going back to roughly 2,000 years, and this is the uppermost floor of the church, but even the uppermost floor is the 12th century, and it's really amazing church to look at, not only because of the kagome structure. So that's the 3-dimensional magnetic structure of the cerium, palladium, aluminum, which unfortunately is not there's no calculation to actually get it. While in the model of frustrated kagome-like planes, due to Nunes Ruggiero and Claudine Lacroix, who is in the audience, they actually worked out in a mean field type measurement involving the nearest neighbor and next nearest neighbor interactions that I showed you, that actually, and also the Kondo effect, they could map out different phase diagrams, and this one would then be corresponding to that of cerium, palladium, aluminum. And these mean field calculations were supported by variational Monte Carlo calculation by Montomo some years ago. But we still don't have a picture, a theoretical picture of the 3-dimensional structure, and I'll come back to that in a moment. Because the question then is, what actually happens to those remaining white ions here? And I've just pulled them out. And if you look at them, they're all frustrated, and that's just a frustrated plane between those antiferromagnetic phases, and they form a rectangular 2-dimensional lattice, and the question is whether they would qualify in this unusual geometry, namely being exposed to magnetic nearest neighbor planes, would then perhaps qualify for a 2-dimensional Ising spin liquid, but up to now that's not known. Okay, how much? Okay, fine. So I come to the last point of my talk. I'd like to just briefly touch upon this field-induced phases in palladium, aluminum. What you actually see, this is a phase diagram that has been formed before. If you sweep the magnetization, it increases with field steadily to about 3.5 Tesla. Then there are 3 different transitions towards a higher magnetized state, and then finally it saturates. And also the resistivity actually shows this type of behavior. And remarkably, in the thermal expansion, you really see these very strong peaks that look first order transitions between the different phases. And that was published just last year. Oops. And what actually then happens is, when you look again at the entropy that is plotted here in this is the phase diagram. The upper one is the phase diagram, temperature versus the magnetic field. These are the three phase lines that I briefly mentioned. And when you look at the entropy, you actually see that actually they accumulate entropy around these phase transitions, as I showed before, and that actually also has led us to define a slightly different frustration parameter than the typical one defining the mean field TC over the real TC. We actually suggest to actually define the entropy by the frustration parameter with respect to the entropy. But since time is running short, I would just like to go back to cerium, palladium, aluminum zero field and compare this with cerium, rhodium, tin. And the cerium, rhodium, tin has been investigated by the group of Tokiwa, Gegenwart, and others quite intensively. And if you look at high temperatures, that is above 1 the curves are very similar. C-axis and A-axis stress actually thermal expansion coefficients are constant, fermi-liquid-like, and also they have the same directional dependence. And if you then look then at the entropy, you see that the change of Kondo temperature or the change of entropy just go in the opposite direction. Things change when you actually go to lower temperatures, because there we have the magnetic ordering that I mentioned. And in cerium, rhodium, tin, you don't have magnetic ordering, although the structure is the same, and also the magnetic anisotropy is the same. So these are the data of Tokiwa and company to expand it on low temperature. That's the divergence in the A direction, and this alpha C over T is constant. So people actually said this is a fermi liquid in one direction. But it's not. It happens when you look at the phase diagram for low temperatures, you actually see, and make the same plots, you actually see that the change of entropy is almost parallel to the C-axis. That is the A-axis, that is in the pure shear stress is almost parallel to the C-axis. And that is the reason why actually this becomes constant. And that's very different for cerium, copper, gold, where I showed this is due to the magnetic ordering. So I showed two examples where one can actually use the thermal expansion to determine the entropy landscape near quantum criticality. There are a lot of enduring questions, but I just leave that open for possible discussions. So thank you very much for your attention.